So again, welcome everyone to our next part of Prague Physical Mathematical Seminar. And we are very glad we can invite for a speech our next speaker, Vladimir Chernov from the Dartmouth College. And he's gonna to talk about causality and Legendrian linking and the compact rank one symmetric spaces. So Vladimir, the floor is yours. And
thank you very much, Yuri, and thank you very much, Roman, for inviting me. And it is my pleasure to give this talk at Prague. I was at Prague many times because my wife, Daria, she was a student at the Charles University for the master's program in archaeology. We are all hoping to visit Prague in person this fall, sorry, this winter already. But things were a little bit different than what we expected. So unfortunately, I'm giving this talk in Zoom, and there will be a second talk about a related subject at the Mathematical Institute in Prague, also in Zoom. I hope to visit Prague sometime in the observable future, and I really like Prague, and so does my wife, of course. So our children did not visit Prague yet, but we hope they will soon. So the talk is based on joint works with Stefan Nemirovsky. Stefan Nemirovsky is working at both Steklov Institute in Moscow and Ruhr University Bochum. And this is as close to the chalk talk as I can get. So I will be writing on the screen. Bochum, of course, is in Germany. So what is the main idea of what I'm going to discuss? So in physics, there is a notion of causal relation. So we all know that we live in some sort of a universe. We don't know what is the topological shape of the universe, but it is something. So causal relation is if one point knows of the other point. So points are called events. And what I'm trying to say is the following, that the speed of light is finite. So if the time difference between two event points is 2 seconds, and the distance between the two events is less than 300,000, less than 600,000 kilometers, which is 300, which is the speed of light times 2, then one of the event points knows of the other point. So it doesn't really mean that the first event provoked the second event, but it means that it could have. So if the time distance is 1 second and the spatial distance is 600,000 kilometers per second, then it is more than the speed of light times 1. So you know for certain that the events are unrelated completely, that they happened independently. So this is what is called causal relation. So if you look at any of the classical books like Hawking and his co-author Ellis on relativity, you will see that this is a classical definition of causality. So what are some of the standard assumptions in general relativity? And this will be the assumptions that I will be working under. So the first assumption is that there is no time travel. So time travel is bad from the philosophical viewpoint because this leads to classical paradoxes. So for example, you can go back in time and try to prohibit your great-grandfather from meeting your great-grandmother. If you succeed, then they never meet. And so in particular, you will never exist and you will not be able to prohibit them from meeting. And if you did not succeed, there is a natural question: what exactly prevents you from prohibiting them to meet? So this causes paradoxes. So one of the standard assumptions is that there is no time travel. And the second standard assumption that people usually make is that there are no naked singularities. So let me talk a little bit more about these assumptions. So can you imagine a mathematical universe, a space-time, where the time travel is permitted? Of course you can, right? I mean, that you can look at a donut, and you can look at the light cones which are circling around the parallel of the torus. Then time travel will be just a longitude on the torus. So mathematically, this is fine. Philosophically, it is not so fine. So this is why I will try to prohibit it. So how do you formalize the notion of speed of light? So there are various vectors. So first of all, what is Lorentz dot product? So in the usual dot product that we teach in calculus, if you want to multiply two vectors, x1, x2, t, say by itself, then the dot product is organized in the way that we all know. So this is x1 squared plus x2 squared plus t squared. In the Lorentz dot product, you put a minus here. So in particular, you immediately get vectors whose dot product with themselves is 0. So for example, 1, 0, 1 dot product with 1, 0, 1 would be 1 squared minus 1 squared. Well, 1 squared plus 0 squared minus 1 squared. So it is 0. So the difference between the Lorentz dot product and the usual dot product is that there are vectors whose dot product to themselves is 0. These vectors are very important. These are the so-called light-like vectors. So if v dot v is 0, then these are the so-called light-like vectors, and they represent movement at the speed of light. So this is movement at light speed. So then there are vectors whose dot product to themselves is negative. And these are the so-called time-like vectors. So this is movement slower than light. So these are the physically possible movements, because Einstein teaches us that nothing moves faster than light. So this is the only thing that can happen. But mathematically, of course, there are vectors whose dot product with themselves is positive. These are the so-called space-like vectors. They represent movement at a speed greater than the speed of light. So physically, this is not possible. So these are space-like vectors, faster than light, not physically possible. So this says what are the light cones in this picture. So this picture has a very realistic time travel trajectory. So in principle, mathematically, time travel is fine. Physically, it is probably not so fine because it leads to paradoxes. What is the second restriction we are going to impose? This is no naked singularity. So let me explain what a naked singularity is. So assume that I look at what is called Minkowski spacetime. So for simplicity, I will look at two-dimensional Minkowski spacetime M11. So this is basically R2 with the dot product, which is X1, T1 dot product with X2, T2 equal to X1, X2 minus T1, T2. So the light cones look very simple. So this is the event point and time goes up. Say, then the light cones are just slopes plus minus 1 originating from this event point. So this is an event point. Now assume that I have an observer sitting here. Then the only thing that this observer knows is the information about the particles located in this cone directed downward. And please interrupt me, by the way, if you have any questions. I think that this is a rather flexible environment. So if you have any questions, please interrupt immediately. So assume that what I do now is that I delete one point. So I delete the point 1, 1. So this point is no longer part of my universe. Then what may happen is that I have a trajectory that ends in the deleted point. And then a very strange thing will happen, because before I reach the deleted point, information from the trajectory does reach the observer. But at the moment when the particle goes into the deleted point, the information stops reaching. So it sort of means that the particle which was moving disappears from our observable reality. Does this happen in real life? Sure, it does happen. But see, the problem is that when it happens in real life, it happens very differently. So when it happens in real life, the particle which disappears from an observable reality does the following, that it crosses the blue cone. What is going on? I think it waits to reload something. Okay. For some reason, my chalk refuses to work. Here it is. So in this situation, the particle disappears from the observer, which is located here. But there is the following situation, and when it disappears from the observer's reality, it crosses the light line of sight of the observer. So this is a light ray connecting the 2 points. So the observer would see the particle disappearing. In this situation, the observer receives information about the particle and then disappears without the particle crossing the line of sight. So this is the naked singularity. And the other thing is not a singularity at all, it is dressed. And there is a natural question, do naked singularities occur? They do, but they occur inside the black holes. right? I mean that it is not completely true that there are no naked singularities in our universe. What is true is that no naked singularities were observed, and this happens really because we don't receive any information about what is inside of the black hole if you disregard quantum gravitation, quantum radiation. So what is a black hole? Topologically, a black hole is very easy. It is just a cylinder or something like that, where the light cones are tangential to the cylinder. So the particles can get inside of the black hole because they are allowed only to travel inside of the cones, but they cannot get out. So this is a black hole, and inside of black holes, many strange things can happen. For example, inside of some of the Kruskal black holes, there is time travel, there are naked singularities, but see, we live here. We live outside of the black holes. So whatever happens inside of the black holes, the information cannot escape. So we don't know what happens there. We can only create a theoretical model. And whatever happens inside does not influence our part of reality, our part of the universe. So Penrose formulated what is called strong cosmic censorship conjecture. Which pretty much says that all the physically reasonable universes satisfy these two assumptions, that there is no time travel and there are no naked singularities. Once again, what it really means is that this would be true if you delete the black holes along the horizons. So I will, for the purposes of this talk, we will restrict our attention to such universes. So to Lorentz manifolds, Lorentz spacetimes, satisfying these two conditions. So condition one is that there is no time travel. Condition two is that there are no naked singularities. So no time travel and no naked singularities. And there is a natural question, what is the name for such objects? And the name for such objects is globally hyperbolic spacetimes. So global hyperbolicity has nothing to do with negative sectional curvature. It just means the following two conditions: no time travel and no naked singularities. So those of you that read Hawking and Dulles' textbook when they were children know that this is not quite the definition from the book. And this is because of the following, that when you say that there is no time travel, this is called causal spacetimes. And the classical definition of global hyperbolicity assumes what is called strong causality, whatever it is. But there is a wonderful theorem of Bernal and Sanchez that pretty much says the following, that no naked singularities condition plus causality implies strong causality. So even though the definition that I'm using right now is not classical, it is equivalent to the classical by the result of Bernal and Sanchez. So there is a classical theorem of Geroch. It says the following: the topologically globally hyperbolic spacetimes look as follows. They are of the form M cross R. So if you want, you can think about this R as time. This is both correct and incorrect. So Einstein teaches us that there is no preferred time, that there are what is called time-like functions. And there is no reason to believe that one time-like function is much better than the other time-like function unless there is some symmetry involved. So this is not quite true that this is time, this is just a time-like function. And this M cross T, so each M cross T is the so-called Cauchy surface. So once again, the word surface is a little bit misleading, because if you talk about the four-dimensional general relativity, which is the universe we live in, then this would be a three-dimensional manifold. But it is still called a Cauchy surface. So what is a Cauchy surface? So I will draw what is not a Cauchy surface. So assume that I have this topological product. So this is, say, a torus. So in principle, you can imagine that there is a trajectory moving at a speed less or equal than the speed of light. So gamma prime dot gamma prime less or equal than 0, which does not close up. So this is not time travel, but it returns to the same surface. So if this is true, then this is not a Cauchy surface. So Cauchy surface means that every trajectory moving at a speed less or equal than the speed of light will intersect it at exactly one point. So this was the classical theorem of Geroch, but we need much more. We would need the theorem of Bernal and Sanchez, which really answers the following strange question, that when I say topologically something looks as M cross R, there is a natural question: do I mean continuously the same as M cross R, or do I mean differentiably the same as M cross R? And the Geroch theorem says that the space-time is homeomorphic to this. So there is no requirement that it is diffeomorphic or differentiably equivalent to M cross R. Bernal and Sanchez proved much more. Bernal and Sanchez proved that it is infinitely times differentiably equivalent to M cross R. So did the physicists know that this would be the case? I guess it depends on whether they can predict the future. Because physicists used the fact that it is differentiably equivalent to M cross R, but it was never proved. There were many attempts to prove that differentiably the global hyperbolic spacetimes were M cross R. Some of the most notable attempts are due to Dickman and Seifert, and they were incorrect. The first time it was proved rigorously was by Bernal and Sanchez. So they appeared to be right. I don't know if this means that they had a time travel machine, they went into the future, figured out that this is a true fact, they can use it. But it is a true fact. It is just that it was proved rather recently at about 2010, I guess, not by Jarosh. And the other thing that they proved is the following, that each M cross T is space-like. That is, that if you restrict the Lorentz metric to the tangent bundle of M, then you get a Riemann metric. Both of these facts are very relevant. So for what I'm going to discuss. So without the Bernal-Sanchez theorem, we would never be able to prove what I'm about to advertise. So assume that I have a Cauchy surface. So I have a globally hyperbolic space-time. This is my Cauchy surface. This is the light ray. So the light ray goes, guess what, at the speed of light. And the requirement of being a Cauchy surface is that every trajectory going at less or equal than the speed of light intersects it at exactly one point. So I take the point of intersection of the light ray with the Cauchy surface. So at this point, I can look at the velocity vector of the trajectory, and I can use the Lorentz metric to orthogonally project it to the Cauchy surface. So this would be, say, black projection to the Cauchy surface. A projection of light ray velocity So I claim that this projection is a non-zero vector. Why? Well, assume that it is the zero vector. So the light vector is null, so it is orthogonal to itself, and it is orthogonal also to the whole Cauchy surface, because otherwise the projection would not be the zero vector. But the Lorentz metric is not degenerate. So it would mean that the velocity vector of the light particle is not only null, it is zero, but it is not zero. So I know that this black vector is not zero. So as you may know, there is no preferred parameterization for the light ray. So different parameterizations correspond to different energies of the photons, but there is no preferred one. So the same light ray can be parameterized in many different ways. This is done by the so-called defined parameterization. So instead of t, you can put a t plus b, so you can shift by a constant and multiply by a positive constant. But what is important is that the direction of the projection of the velocity vector to the Cauchy surface is intact. So this does not change. The direction of the projection of gamma prime to Cauchy surface. And as I'm trying to say, there is no preferred parameterization. So what it means is that I need to introduce a new space. So if X is a space-time, globally hyperbolic space-time, so satisfies conditions 1 and 2, And then I can introduce a new space, which is space of all future directed light rays. And each future directed light ray, because it does not have a preferred parameterization, gives me a vector tangential to the Cauchy surface. I can choose a different parameterization. I will get a different vector, but with the same direction. So what I get is that the space of light rays is what is called the spherical tangent bundle of the Cauchy surface. So this is the unit tangent bundle. So looks great, but this is unfortunately not what we want. What I really need is that I need to use Bernal-Sanchez theorem. So you know that if M is Riemann, then tangent bundle of M, which is the all tangent directions, is the same as the cotangent bundle. In the same fashion, because of the same reason, if M is Riemann, then the spherical tangent bundle is the same as the spherical cotangent bundle. So the space of all directions of functionals can be identified with the space of all directions to the Cauchy surface, tangential to the Cauchy surface. And guess what? If you go back in time, which is prohibited in physics, but allowed for our purposes, we see that Bernal and Sanchez proved that each Cauchy surface is Riemann. Right? So it means that the simplification is correct. The space of light rays is canonically identified with the spherical cotangent bundle. So on the first glance, who cares? Because what is really the difference between the spherical tangent and the spherical cotangent bundle? It seems to be almost irrelevant, but it is very important for what is about to happen. Because this guy has a natural context structure. So in physics, you are probably very well familiar with symplectic forms because they appear all the time in classical mechanics. Quantum structures is the odd dimensional analog of symplectic structures. This is both symplectic and quantum structures is what Roman Golovko and I do. So we like them a lot. But let me give the strict definition. So quantum structures exist only on not-dimensional manifolds. So Z to K plus 1. If the manifold is even dimensional, it could not have a quantum structure. In the same fashion, if the manifold is not even dimensional, it could not have a symplectic structure. Symplectic structures appear naturally in classical mechanics on the phase space. Quantum structures appear when you talk about light propagation, so geometric optics or light in general relativity. So what is a quantum structure? So quantum structure is the following. That this is a hyperplane distribution so at each point of your manifold, you have a hyperplane. So here it is like, say this, and here it goes a little bit down, and here it goes a little bit up. And this is not only a hyperplane distribution, this is what is called a Quarian hyperplane distribution. So there is a preferred half space. Now, if you have a hyperplane, it can be visualized as the kernel of some function. And the half space which is preferred is the half space where the functional is positive. But now I have such a hyperplane with the preferred half space at each point of my manifold. Right? So at each point it gives me a functional. So altogether I get a one form. Where do I cheat? Well, the functional defined by this information is not unique. If I multiply the functional by any positive constant, I will get another functional with the same condition. So this one form alpha is not unique, but you can still check that it satisfies the following condition, that alpha wedge d alpha to the power k is non-zero. And this is what makes it a contact form. So this is alpha is a contact form. And the kernel of the contact form is a contact structure. Okay. What does it mean geometrically? You know, there is a Frobenius theorem that says that if the B brackets between the vectors on my hyperplane field are zero, then I can choose a surface which is everywhere tangential to the distribution. This strange condition means exactly the opposite, that the dimension of tangent submanifolds is as small as possible. So the maximal tangent dimension is k in Z2k plus 1, and such objects are called Legendrian submanifolds. So submanifold is Legendrian if it is everywhere tangent to the contact structure, and if it satisfies the condition that it is a k-dimensional submanifold in a 2k plus 1 dimensional manifold. Does this make sense, or I already lost the audience?
I think it's clear.
Okay. So this object is a contact manifold because it has the so-called Liouville form. And this means that the space of light rays has a natural contact structure. So this was observed by Robert Lowe, a student of Penrose. So the space of light rays has a natural contact structure. Let me observe that the space of light rays is identified with a spherical cotangent bundle of the Cauchy surface, but the identification is a little bit tricky because if I look at the globally hyperbolic spacetime and I look at the Cauchy surface M1 and the Cauchy surface M2, it is sort of tempting to say that the spherical cotangent bundles are identified by the parallel shift. That you just flow one of them to the right if they are parallel, and you get the contact structure in another one. This is not the case. What happens in reality is that the light ray crosses the first Cauchy surface somewhere here, then it travels, crosses the second Cauchy surface somewhere else, and the identification between the spherical cotangent bundles of two Cauchy surfaces is quite unnatural. But the contact structure you get on the space of light rays is natural. So there is no preferred time-like function, so you cannot say which Cauchy surface is better than the other Cauchy surface. All these notions do not exist. But the notion of a natural contact structure of the space of light rays does exist. So there is a natural question, how many light rays pass through a point? And everybody in physics knows that the answer is the light cone. This is not the light cone I was drawing before. This is the exponentiated light cone, if you want to talk mathematically. So in particular, it has various singularities. Right? Due to the effect of gravitational lensing, it is not true that two light rays which originate from the same point never meet. They do meet. And in particular, this is why when you look at the sky, sometimes you think that you see 5 stars, but in reality, this is 1 star. It is just that the light is coming from 5 different directions into your eye. So the light rays form a light cone, but this is not what is going on. What I would like to do is that I would like to look at the same light cone in the space of all light rays. So in the spherical cotangent bundle of the Cauchy surface, this is identified with the space of light rays. What I get is not a cone at all, I get a sphere. So how do you see this sphere? Well, assume that you're a small human being, and I give you a laser pointer. So this is my laser pointer, and I ask how many directions can I point around me. That's, of course, is a sphere. I can point it in any direction around me, and this is the sphere I'm talking about. So this sphere is Legendrian. This was observed once again by Robert Lowe. So what it means is that if I have two event points, P and Q, I get two Legendrian spheres. So once again, Lowe observed that this sphere of light rays through a point is Legendrian. So 2 points, 2 spheres. And guess what? 2 points can be causally related or not. So causal relation, once again, means that one of the event points emitted information that reached the other point, and causal unrelated means the other way. So what we proved essentially is the following. So theorem. The 2 points are causally related. If and only if the Legendrian link consisting of spheres of light rays through the 2 points is non-trivial. So this reduces the question about causality to the question about Legendrian link. So contact structures is once again what creates the Legendrian linking. This is what Roman Golovko does. This is what I do. And this is a complete reduction of the study of causality in general relativity to Legendrian linking question. Now, of course, this is a theorem, so it needs certain conditions. So provided that the following conditions are met. Either the universal cover of the Cauchy surface is non-compact, so let me underline the word not compact. Or two, so assume that the universal cover is M tilde, the integer cohomology of M tilde is not the one of the cross or the compact rank one symmetric space. Okay. Now let us think. So assume that we concentrate our effort on 3 + 1 dimensional spacetimes. So the question to the audience is, how many simply connected manifolds, which could be universal covers of anything, do you know such that, so what can you tell me about a 3-dimensional manifold M3, which is closed, compact, without boundary, and it is simply connected, so it could be a universal cover of something? How many such manifolds do you know? Well, the unanimous response from the audience, I guess you're muted, so probably this is why I don't hear your answers, is the following, that the Poincare conjecture proved by Perelman, who followed the Hamilton program, says that under these assumptions, M is a sphere, is a 3-dimensional sphere. So the only 4-dimensional manifolds where Legendrian linking is not the same as causality are those where the Cauchy surface is universally covered by a 3-dimensional sphere. So basically these are land spaces, and pretty much this is it. So what about higher dimensional objects. Right? I mean that, okay, in physics, you know that space-time is 4-dimensional, but mathematically you can talk about 17-dimensional space-times. So it could be that the universal cover of the Cauchy surface is, I don't know, CP2 cross CP2.
Yeah.
Yeah, so are you talking now about like the counter examples where the theorem is not true?
The theorem says when linking is equivalent to causality, right? So I'm underlying the word not because of the following, that usually in mathematics, you want something to be compact. Here it is the other way around. As soon as the universal cover is not compact, linking is the same as causality. If the universal cover is compact, linking could be the same as causality or not, but if the integer cohomology ring is different from a compact rank 1 symmetric space, then linking once again is the same as causality. So I can completely reconstruct causality from linking. So what are compact rank 1 symmetric spaces? These are basically projective spaces. So the Hamiltonians, the Octavians, and so on. So there is a natural question, are there any manifolds which are not homeomorphic to a compact rank 1 symmetric space, but are simply connected and have the integer cohomology ring the same as of the compact rank 1 symmetric space? Nobody knows. Nobody knows the answer to this question. So it could be that we prove that the only bad scenarios are the scenarios when the Cauchy surface is a compact rank 1 symmetric space, but we cannot claim this because there is no geometric theorem which we would need to use. Now, what happens if the Cauchy surface is a compact rank 1 symmetric space?
Basic question. So these conditions that you provide, he knows that they're essential. Basically,
I cannot hear you, sorry.
So my question is, like, you have these two conditions, right, in the theorem. Like,
if any one of them holds, then linking is the same as causality.
Okay, so you know that these two conditions are actually essential, right?
I cannot hear you again, sorry.
Maybe I mean, you know that they are essential. So they are not technical, they are essential.
They're essential, this is what I'm trying to say.
Okay.
Assume that M is a compact rank 1 symmetric space. Assume, for example, that M is a 2-dimensional sphere. And what I would like to do is that I would like to look at a space-time which is S2 cross R, so it is globally hyperbolic, with the following Lorentz metric. Round metric on a sphere of unit length plus minus dt squared. Then there is a standard trick question. How do you relate the sphere of light rays passing through the North Pole 0 and the sphere of light rays passing through the North Pole 2 pi? And the answer is that this is the same sphere, right? Because this is a product metric. So light ray means that the component along the sphere is the same length as the component along the line. So as soon as line goes 2 pi units along the line, the trajectory will go around the great circle around the unit sphere. So all the light rays through North Pole 0 will pass through North Pole 2 pi. And this is called strong refocusing, once again, due to Robert Lowe. Because all the light rays through 2 points are the same. And I'm trying to round up, so I hope to be done in 2 to 3 minutes. So what I would like to do is that I would like to ask you a question. Assume that I look at the following sphere, South Pole 2 pi. and I look at two events points, North Pole 0 and South Pole 2 pi. Are they causally related? Yes, right? Because I can go along the light ray from North Pole 0 to South Pole pi. Then I can stop movement in the spatial sense and I just fly along the time direction to South Pole 2 pi. So these two are causally related. But these 2 points are causally unrelated because they live on the same Cauchy surface. So they belong to the same slice of a time-like function. But what is going on? So these spheres are the same because all the light rays through North Pole 0 pass through North Pole 2 pi. And these spheres are the same because they even have the same name. So on the sphere cross R, there is no hope to say that linking is the same as causality because I just gave you a counterexample. I have two links which are exactly the same, but one link corresponds to causally related events and the other corresponds to causally unrelated events. And of course, it is not too hard to convince yourself that this has nothing to do with the sphere. It has everything to do with refocusing. So as soon as you have refocusing of light rays, which would be passing from one point to another, all the light rays through one point pass through another point, you will have such an example. And for compact rank 1 symmetric spaces, you always can construct such examples. So basically, with some hope, we prove that if the Cauchy surface is not a compact rank 1 symmetric space, then linking is the same as causality. If it is a compact rank 1 symmetric space, there are always counterexamples. The gap is once again the following, that nobody knows if there are any examples of topological manifolds which are simply connected, have integer cohomology ring of a compact rank 1 symmetric space, but are not homeomorphic to a compact rank 1 symmetric space. So what does this result mean from the point of view of science fiction? It means the following, that you can completely reconstruct this linking from the Cauchy surface at any time moment. So you can basically reconstruct the linking from the universe as we see it today on December 9th. So assume that you are the creator of the universe. You want to go back in time and you want to change the causal relation between any 2 points so that today the universe looks exactly the same. The answer is that you would not succeed because linking is the same as causality. Linking is completely determined by the current picture. So the only way for you to allow yourself to do such tricks is to create the universe from the very beginning so that the Cauchy surface looks as like a compact rank 1 symmetric space. And this is where I would like to end. So are there any questions?
Thanks very much for nice talk. Please.
So do you have an expectation for the geography of such links?
Well, I mean, topologically, all Brownian links can be realized this way. In terms of Legendrian linking, this is a wide open question. So what we proved with Inna Pitkova and Gage Martin is that Havanov homology or Higer-Floyer homology completely determines causality. But this is for time models of 2 + 1 dimensional spacetimes. So for 2 + 1 dimensional global hyperbolic spacetimes, completely determines causality. If you want to do this in high dimensions, you will probably need to do Morse flow trees, which were developed in the works of Ekholm, Ivan Smith, and others. As to what is the geography, I mean, all Brownian links admit Legendrian approximations, so I mean, there are many such links. So what would be the other questions?
Legendrian approximation basically do approximation with the loop mechanics, so somehow, or to something which is flexible in some way. So somehow.
I'm sorry, I cannot hear what you're saying. Can you ask Yuri to repeat?
Maybe I can say this way and so what I'm saying is that in order to do the approximation, usually you approximate something flexible in some way. I don't know, it's a loose one or it's a stabilized one. So my question is somehow about the, I don't know, about the rigid type representatives, like whether you can say something about the geography of
well, let me try to say the following, that if you ask yourself about, so this is a point on the Cauchy surface. Assume that the event point happens on the Cauchy surface. And then the Legendrian sphere you're talking about is the fiber of the Cauchy surface, of the spherical tangent bundle of the Cauchy surface. So all the links that you need are links where each of the components is a fiber of the spherical tangent bundle of the Cauchy surface. You don't need any other links at all. These links can be linked topologically or Legendrian. Eliashberg and Chernov proved that Legendrian link theory is much more complicated than the topological link theory. So Low, when he was creating all the subject, he had a counterexample, because he, of course, wanted to show that topological linking is the same as causality. And he had a counterexample. This counterexample is just the following, that you take this picture and you rotate it around this. I'm sorry, I should draw it bigger. And you rotate it around this axis. So you will get a wavefront. This is the first of your Legendrian knots. So the second Legendrian knot is obtained by rotating this picture. So a small circle here. So this picture will be topologically unlinked, but Legendrian linked. So he got this example and he thought that this means that in high dimensions, there is no hope for linking to be the same as causality, but this is because Eliashberg and Chernov did not develop Legendrian link theory yet. And later came Jose Notario and Paul Todd, other students of Penrose, and they asked the same question in the Legendrian category. And I have to warn you that if you look at the papers of Notario and Todd paper is dealing only with the situation where the Cauchy surface is R3. So they conjecture that when the Cauchy surface is R3, then Legendrian linking is the same as causality. Low conjecture that if the Cauchy surface is open, so it is not a closed two-dimensional manifolds, but it has to be two-dimensional, then topological linking is the same as causality. What we proved is much more. We pretty much proved that unless the universal cover is compact with very specific integer cohomology, linking, Legendrian linking is the same as causality. right? So this is why in the example created by law, which I try to draw here, it is a counterexample to the topological conjecture of law, but not to the Legendrian law conjecture of Nattario and Todd. But what we proved is much more than they ever hoped. Because Nattario and Todd was asking only about the case where the Cauchy surface is R3, if you talk about four-dimensional gravitation. We proved it for all cases where the Cauchy surface is anything you want, other than when it is covered by a three-dimensional sphere. So are there any other questions?
Maybe I have a question. I probably missed something, but did you somehow define what's the strong causality and how?
No, I did not define strong causality. I just said that in Hawking and Dell's book, globally hyperbolic spacetimes are strongly causal spacetimes without naked singularities.
Mm-hmm.
And Bernal and Sanchez proved that this definition is equivalent to causal spacetimes and no naked singularities.
Yeah.
So I'm not using the definition of the Hawking Dell's, I'm using the equivalent definition, which is equivalent to the classical one by Bernal and Sanchez. And this allows me not to discuss what is strong causality.
Yeah, okay. And the result of Bernal and Sanchez implies that if we assume we live in a strongly causal space-time, there must exist globally defined time, because
this too, yeah. This is a different result of Bernal and Sanchez, but they proved it too.
Yeah, because
it is not a preferred time, right? I mean, it is just a time-like function. It is not true that you have a preferred time. There are many.
But once you consider space-time as a Cartesian product of two spaces.
But I do not consider space-times, which I consider them as a topological Cartesian product, not as a Riemann Cartesian product. There is no assumption that the Lorentz metric is nice.
Okay.
It can be warped, it can be any globally hyperbolic metric you want. The only assumption, the only conclusion of the Bernal-Sanchez theorem that topologically your space-time is M cross R.
Mm-hmm. Mm-hmm.
It does not say that it is geometrically M cross R or anything like that.
Okay. And the novelty of their result is that it inherits C infinity structure of
yes.
this
of the product, yes.
Of this product. Okay. Mm-hmm.
Just one remark. So probably you know that there is a version of Hegel-Floyd theory for high dimensions, which is a project basically of Honda and Quarian. I'm not sure like how exactly you use this color and the other collaborators.
You mean the result with Petkova and Martin?
Yeah. So somehow there you use, so you said that in particular homology.
This is because of the following, that so basically everything can be reduced to the situation where the Cauchy surfaces are R2, because otherwise you deal with the universal covers. When the universal cover is R2, the space of light rays is a solid torus. And the solid torus can be visualized as R3 or S3 minus the red circle, right? If you delete the red circle from R3, you get a solid torus topologically. So there is a result of Baldwin in the case of Heger-Floyer homology and of Z and Zhang in the case of Havanov homology, which says the following, that if you look at the following very trivial link, so this is one component, This is another component. And the third one is the circle. Then Khavanov homology distinguishes it from all other three-component links. But this is exactly the link that you will get for causal and related events. Once again, this third component, which will be black in a second, so black, is needed to get R3 from R3 to the solid torus. The linking theory by our theorem with Nemirovsky happens in the solid torus, but Khavanov homology happens in R3. So you need something to get from R3 to the solid torus, and you delete the black circle. So then instead of getting two-component links, you get three-component links. And the result of Z and Zhang says that Khavanov homology distinguishes this specific three-component link from all other three-component links. And the similar result by Heeger-Floer homology is due to Baldwin. And this is why you get that Heeger-Floer and Khavanov homology completely capture causality.
Is there any other question? Doesn't seem to be the case, so thanks to speaker again.
And I'm going to give a talk at the Mathematical Institute, which will be some sort of informal continuation of this talk. So I mean that it is not required that you attend this talk for the second talk, but they're philosophically related. So for example, the speaker is the same. Yeah. So it was a pleasure to see you all, and I hope to come to Prague in some observable future. And that's it. Have a nice day. Thank you for the
very
nice
much.
questions.